the Australian Museum has some large and very important geoscience collections. So I want to talk about some of these and to give you two examples, one from the mineral collection, one from the rock collection, about how these specimens can be used to extract information about how climate has varied in the fairly recent geological past. Now, in the late 1970s, the Australian Museum gained the 200-piece rock collection and field notes from an expedition mounted in 1947-1948 by James Lambeth. And this was to Heard Island, which is a sub-Antarctic island. It happens to be a volcano. I suppose it would be no exaggeration to say that the local weather is extreme and that access is difficult. It is situated in the Southern Ocean, about 400 kilometres southwest of the coast of Western Australia. It's one of these hotspot basaltic volcanoes and emerges from the sea floor and forms a volcano which is called Big Ben. It rises to 2745 metres to the summit, which is called Mawson Peak. Now, the island supports extensive glaciers that descend from about 2,400 metres down to sea level, and they form extensive ice cliffs. The glaciers are recorded as retreating since measurements from the 1850s, and retreat rates are indicators of both climate change and volcanic eruptions acting together. There are also small scoria and tuff ash cones around the perimeter of the island, and they are probably younger than about 10,000 years. Now, there's a new study on the rocks that are in our collection from this site by a PhD student, Jodie Fox, from the University of Tasmania. And she's going to use a variety of methods, including strontium isotope and other chemical analysis methods on these rocks to find out clues to variations in former ice cover thicknesses and sea levels, to partly reconstruct some recent climate changes and some of the recent volcanic history. These measurements will be made on lavas which have been previously erupted underwater or under ice, and these give distinctive molten lava and water interactions which will be shown by chemical signatures. The second example I want to give is from limestone caves. Limestone caves are time vaults or time capsules which preserve climate data within their calcite formations. Calcite formations, or any formations in caves in general, are called speleothems. So this data is locked up into the cave formations themselves and in successive layers of calcium carbonate which build up over each other and have slightly different chemical or isotopic compositions or ratios which can be measured, and these can be used as climate proxies to reflect changes in the world above the caves and changes in the drip water which is coming down into the caves from above. This is a bit like measuring annual or seasonal growth rings on trees. If you slice a stalactite or stalagmite through, there are various layers which can be analysed. Now, stalagmites are preferred for study rather than stalactites because they give a much more continuous seasonal or annual climate record, and the rings are more widely spaced and easier to see and to study. But stalactites, ones that come down from the ceiling, can also be used to give useful data, although it's a little discontinuous. So what are the measurements? Well, they are isotopes. We measure uranium, thorium and lead isotopes, or luminescence studies, or palaeomagnetism. And these can give the ages of the cave formations and help to establish a time series. If you measure the ratios of stable oxygen and carbon isotopes, these can correlate to major trends like high or low rainfall, warmer or colder periods, and surface vegetation cover over a time period of thousands of years to maybe 500,000 years to reconstruct recent climate changes. On the slide there you can see a stalagmite sliced through, and you will see curves of variations in carbon and oxygen isotopes against a time scale, which also shows historical events, such as the Little Ice Age, the medieval warming period, and the Dark Ages. This is how it works. In dry years, stalagmites contain more of the rarer, heavier oxygen-18 isotope. And this isotope is less likely to evaporate in a dry period than the lighter, commoner form of oxygen, which is oxygen-16. Also, trace amounts of magnesium increase in dry conditions and decrease in wet conditions. Now, these isotope methods have been widely used in Europe and North and South America, but so far there have been very few applications to Australian sites, mainly by CSIRO, ANSTO, and Universities of Sydney, Newcastle, New South Wales. There's been only limited use of these isotope methods at Jenolan and other New South Wales cave systems, so there is scope for further collaborative studies using material in our existing collections and newly collected material. Thank you.